This episode is brought to you by IBM. TWIML listeners are invited to join the Florida Hacks with IBM competition to grow their data science portfolios and skills. Build a solution to help combat climate change with mentoring from climate and IBM technology specialists. You'll get free access to IBM cloud services, including popular data science tools like Watson Studio, Watson Assistant, and Watson Discovery. Registration is free, and your solution could win part of the $100,000 prize pool. To learn more, visit twimlai.com/Florida-IBM. Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Thanks so much for joining us. And if this is your first time, I invite you to hit subscribe in Apple Podcasts, Spotify, YouTube, or wherever else you might be listening to the show. All right, everyone. I am on the line with Yejin Choi. Yejin is a professor at the University of Washington. Yejin, welcome to the TWIML AI podcast.
I'm excited to be here. Thanks for having me.
I'm really looking forward to digging into our conversation. I'd love to have you start by sharing a little bit about your background and how you came to work in the field of AI.
Right. So I primarily work in the area of natural language processing, but like any other subfields of AI, now the boundaries become looser and looser. And I'm excited to work on the boundaries between language and vision, language and perception, and also thinking a lot about the connection between AI and the human intelligence and what are the fundamental differences in that in terms of knowledge and reasoning.
And so let's go a little bit deeper into that. Talk us through like some of the ways that you take on those topics in your research portfolio. What are some of the main projects you're working on and the things that you're exploring?
Right. So currently, I'm the most excited about the notion of common sense, knowledge, and reasoning. This was, in fact, the early dream of AI field. In 70s and 80s, people loved to think about it and try to develop formalism for it. It turns out it's really trivial for humans, but really difficult even for the smartest people to really think about how to define it formally so that machines can execute it as a program. So for a long time, scientists assumed that it's a doomed direction because it's just too hard. So AI didn't really thought about common sense for a long time. And then it's only in recent years, some of us got excited to think about it again, which is in part powered by the recent advancements of neural models that is able to understand large amount of data.
You talked a little bit about the difficulty of, or you referenced the difficulty of defining common sense reasoning. How do you define it?
Right. So I take a broader definition such that it's everyday knowledge, practical knowledge that most people share in order to function safely and reasonably in our everyday lives. So for example, in general, it's okay to keep your closet door open for a while, but not as okay to keep your fridge door open for a while. But of course, I can add additional context to make this inference feasible. So if the refrigerator is new, unplugged from the wall, there's nothing inside, then who cares? And again, the closet, if there are rats around, you might want to close the door. So it's almost like rules of thumb that we live by. But the hardness of it is that it's very contextual. And depending on your cultural backgrounds and everything, the judgments could change. And yet it seems that there are this common ground that a lot of people agree with. And so that's my working definition of common sense.
Okay. You described it as rules of thumb. How important is the notion of rules in that? And I'm thinking about that relative to, we spend a lot of time thinking about deep learning and deep neural networks and in some ways there may be more pattern-based than rule-based. Is there a notion of fundamental foundational patterns as being akin to common sense, like the low layers of a neural network learning textures and things like that? Is that kind of common sense in a sense?
Yeah, absolutely. And that's a really sharp question. I appreciate the question. In fact, when I say rules, I use the word very differently from how more formal approaches in AI mean by rules. So what I mean by rules is really through language. I can describe my rules through language, but you can immediately imagine that these rules are just natural language rules. So there's always a different interpretation you could do. These are just generally true statements, but it may or may not be true. And it also includes just a declarative knowledge about, for example, sky is usually on top of my head. It might change depending on my location, of course.
Mm-hmm.
Usually it's blue unless it's red in the evening. And so we have a lot of this knowledge about, I would be surprised if the sky was suddenly pink, because that's less expected. So there's this expectation about how the physical world works, how the social world works. And some of this, a lot of this is what, as a human, we just have this memory of how the world works. The machines today, not as much. If you ask a GPT-3, for example, how many eyes a horse has, it might say 3, primarily because people usually don't talk about how many eyes a horse had when they see a horse or ride a horse. They never mention it. It's too obvious. Yeah. So yeah, it's very elusive. It's in my work, it's all in natural language, or in large part, it's in natural language, except when I'm grounding it with vision.
So how would you articulate the current state of the world or research frontier in terms of common sense reasoning? How far along are we?
It's a bit of a moonshot research, I should mention still. But I think we're seeing the most exciting results, I would dare say, than ever before, because in my group, we have some research demo running online. It's a model called COMET. It means Common Sense Transformers, built on top of transformer neural language models. And it's able to make common sense inferences about random situations that you might encounter in lives. And what's fascinating about that system is that it has learned from symbolic knowledge graph of some common sense rules, not all, because there's no way we can enumerate them all. And I don't think humans actually really learned from enumerated rules. But what's exciting about current neural language models is that they can generalize out of that symbolic knowledge graph so that it can reason about new events that was never taught directly before. And oftentimes that reasoning is very surprisingly good. It's not perfect yet, but it's a running system that demonstrates the new capability that we've never seen before.
Can you give us a concrete example of the specific task and the kinds of results you're seeing?
Sure. It's actually the best to describe the 3 examples. So if somebody is repelling somebody's attack, it's not very contextualized event. I might say person X repels person Y's attack. Usually we might think, X might be a strong person to fight back because I might just run away. And maybe Y did something wrong. Probably Y attacked beforehand. So we can reason about preconditions, post-conditions, and causes and effects, their motivations and their mental states. Probably X is unhappy about the situation. And if X successfully repels Y's attack, Y might either attack back or run away. Unlikely that suddenly Y brings a gift and, suddenly celebrate, right? So there are uncertainties about the causes and effects and what might happen before and after. However, we have a reasonable expectation about what are the likely things to happen. So this particular event was in our symbolic knowledge graph, but what's not in the graph that somebody gave me as an adversarial problem to challenge my model was, what if somebody repelled someone's attack in a chess game? Now, that's a very different situation where it's not about fist fight situation anymore. It's really intellectual fight. And our model was able to somehow make an analogy between the two very different situations. And now the model inference is all about having maybe chess game beforehand. Maybe the person is very intelligent, smart, clever person and things like that. So the generalization here is quite exciting.
Mm-hmm, mm-hmm. So in this example, you mentioned that something was in your knowledge graph. What specifically is in the knowledge graph?
So given any center event like a person X repels a person Y's attack,
Mm-hmm.
in our original atomic knowledge graph, we had 9 different inference types, which is generally about people's mental states before and after, what they might want to do before and after, preconditions and postconditions, and things like that. In our later atomic knowledge graphs, we expanded that to include 24 different inference types. In the original version, it was very human-centric activities that we had as a knowledge graph, but now we also include object-centric knowledge as well as event-centric knowledge as well. So that's what's in the graph. And the graph has at the moment 1.3 million if-then rules in natural language. So if this happens, then something else might be true, likely to be true.
Mm-hmm. And are the if-then relationships, are the conditions, the if conditions and the eventual outcomes represented is that an atomic unit within this graph, or do you have a bunch of conditions and a bunch of outcomes and the graph links those?
Yeah, that's a great question. They are all open free text, short natural language phrases,
Okay.
and they're stored as if they're in a graph structure. But in fact, we are going with natural language as much as possible. There's no logical forms or anything.
Okay. Okay. Interesting. Interesting. In hearing you describe the scenario and the example, I couldn't help but think about a relationship between kind of this common sense reasoning task and, in a sense, like storytelling, creative storytelling. Like you pose this scenario and then you're like, what if this happened and maybe this happened and this happened and this happened and all the things that we might expect an author to do to build a story. Is that something that you explore at all? What do you think about that relationship?
Absolutely. Yeah, I'm amazed by your question. So, in fact, counterfactual reasoning, what if something else happened? That's really essential part of our reasoning capabilities. And when I think about human reasoning, it's really fascinating because we can also do a lot of the times what I call, what researchers call as abductive reasoning that was originally proposed by Peirce long, long time ago. So he was a philosopher, and this is abductive reasoning or abduction is about reasoning about the best explanations given partial observations. And that's really important aspect of storytelling and story understanding. So, normally when we watch a movie, we might be sitting for 2 hours that might describe a story that happened over a decade, for example.
Mm-hmm.
We do not need to see all the minor details of everybody involved in the scene because we can connect the dots. We can reason about what's not said because in our mind, it's obvious. That sort of a reasoning is abductive reasoning in that we sort of fill in the blank all the time. Sometimes, like another example is you come home, suddenly windows are broken in your house. They were okay in the morning. Then you might infer that maybe thief came in. You don't know for sure, but
Right.
this almost like pops in your mind right away as opposed to you considering all the other million things that may have happened. It's almost like we instantaneously have this ability to reason about what's the best likely explanation to a scenario. And basically what Comet, the common sense transformers, try to do is like a smaller unit of that sort of a rich reasoning people do. And so I also work on abductive reasoning as well as counterfactual reasoning, as well as storytelling. And in all of this, I try to think about these smaller units of reasoning in the form of basic, more lower level common sense inferences.
Mm-hmm. Mm-hmm. Talk a little bit more about Comet. How do you apply transformers to these types of problems?
Yeah, that's a great question. So Now we are entering this knowledge integration. When we have this knowledge, how do we integrate for reasoning? The more I work on these areas, I realize that the distinction between knowledge and reasoning, this is in a continuum as opposed to them being two entirely different things. In the following sense, a lot of the times our reasoning is almost memorized knowledge. We don't always recompute the whole thing. Anything we computed often enough, we already stored in the background knowledge. So it's a combination of the two. The more the model memorized, the more likely that it performs better, even for new situations, because it's able to draw a lot of analogy. Perhaps it's just similar to how humans who read a lot of books probably not guaranteed to be the best in an exam or, writing a book, whatever, but it probably doesn't hurt. It only helps. So that's that. And when we actually, in a technical sense, integrating knowledge, it can be done in many different ways. Sometimes we just provide it as additional textual input for any given QA problems. Some other times we can integrate that at the continuous level or neural level, at the neural representation level. And even for that, there are many different ways of doing it. We could do it more deeper integration with many layers of transformers, or we could do just at a shallow level at the input-output layers. So people are trying different versions. That's what we have tried so far.
And so how do you, in your case, how do you prepare your data to train a transformer model around these types of problems?
Great question. So didn't talk about that at all. Comet is basically starting from off-the-shelf neural language models that have already read a lot of raw data. And then we compile atomic knowledge graph as if it's just additional a string of a text. So the Comet is reading atomic knowledge graph as if it's just natural language sentences. And we found that by doing so, the model is able to draw or connect to the dots between the implicit knowledge in the raw text with more explicit knowledge in the knowledge graph.
And when you say that Comet is reading that, is this a training time, or is this your conditioning text when you're doing an inference against your model?
Yeah, that's just during training time, so that during inference can operate in a similar way. So given some context, it can then reason about whatever common sense relationship, inference types that we want to look at.
And I guess I'm trying to get to the relationship between some kind of formal reason, not formal reasoning in the sense of academic formal reasoning, but something that is where there's some actual reasoning happening, as opposed to a language model spitting out text based on stuff that it saw that was based on these relationships, if that makes any sense.
Yeah, that's a great question. And it's a very, it's a question that, okay, now I'm going to say something that some people might disagree with, but so I think a lot of academics have this romantic viewpoints about reasoning. It must be something that I cannot easily do, but computers can do in a very accurate, precise manner. And we should be able to somehow come up with some logical formalism that really spells out all this inductive, deductive reasoning that we did in the process. So I think that was actually the reason why in 70s and 80s, the common sense research didn't go very well, because the researchers back then were a bit too hung up on having to come up with this formal language, logical forms, or some sort of a logical formula that can describe the sort of things we can reason through language. So I came to this conclusion in recent years that actually language is the best medium for reasoning. In fact, even mathematicians, they cannot do very much of a proof without access to natural language. If you ask those people who do this all the time, they actually think also a lot through language, and they have to explain what their formula is supposed to mean through language. So even if they have equations and logical forms that they define, they really cannot do very much without language. But when we think about how humans learn and how we argue with each other to share our reasoning about an issue, everything is through language. And the moment we try to invent some other formalism there's a loss of information or loss of expressiveness. That loss is so significant so that it may be okay if I want to only focus on integrating some equations or differentiating some equations. Then it's okay to lose the power of natural language. But if I want to do social common sense reasoning, physical common sense reasoning that I can describe in natural language and all of it, then we are getting into trouble when we try to translate that content down to some mathematical formalism, because we never been able to invent such a language that's equivalent to the power of language.
Mm-hmm.
Part of the problem is that natural language is a bizarre thing. It's just oftentimes ambiguous, which is also why, there's a major discrepancy in the way how people might, even with the science, how people interpret whether climate change is happening or not, whether vaccine works or not. One would expect that it's a scientific result, so everybody must be able to interpret it in the same way, but actually not. So that's a part of the challenge. And it seems that we just have to embrace it when there's an ambiguity, instead of trying to invent a language that does not have any ambiguity, it might be that the AI agent has to be able to work with it. Mm-hmm. So it's a very experimental research direction, I would say, but empirically, it's been the most promising of all.
I think what I hear you saying, or at least the conclusion that I come to based on what you're saying, is that kind of going back to using the transformers and language models as part of these common sense reasoning tasks, is that, to put it simply, like the way you evaluate whether common sense reasoning is happening is if the result that you get is reasonable and not based on some other kind of formal structure. You just have to evaluate the results as opposed to applying some kind of formalism or analysis to the method.
Yeah,
and I'm not sure I agree with it seems like that leaves a lot to ask, but is that essentially kind of the direction you're going?
Kind of. Probably yes, in the sense that, this is generally a question against the deep learning altogether, though, in that, can it drive a car by actually learning how to drive a car or can it translate language from one language to another by actually understanding any of those languages, or it's just learning the surface pattern matching? And so right now, everything is surface pattern matching.
Sure, but I think the difference is in the language translation, the task is language translation, and we can, we're only evaluating whether the network is translating the language. Here, you're saying that the task is, or the objective is, reasoning. And so how do we evaluate if the system is doing reasoning as opposed to doing some task?
No,
that's a proxy for reasoning.
It's like pretending to be reasoning, but so long as the common sense inferences that it spit out looks commonsensical, then we are happy. And the model performance keeps increasing when judged by humans on events that it's never seen before. So we usually only evaluate on events that are brand new, because what's the point of memorizing what was in the training data? So when we do that, so the first time Comet came out in the world was 2 years ago. So every year we see some considerable improvement, and it's been only 2 years. Machine translation, people worked on it for more than a decade. So let's not lose hope too soon after 2 years. But machine is not really translating either. This is a philosophical argument, but and I want to redefine reasoning a little bit better, because there's an intuitive reasoning, that's never guaranteed to be correct. And that's primarily what common sense inference is all about. Because, when you reason, oh, maybe somebody broke into the house and stole anything, how do you know for sure? You cannot know. So the real correct inductive or deductive reasoning should not allow you to make any judgments whatsoever. But then, how do you live at all? How do you understand story? Because story understanding is all about abductive reasoning as opposed to inductive or deductive reasoning. When people think about the correctness of reasoning, oftentimes they're equating that with induction and deduction, which feels more intellectually reasoning like, because we are more exposed to it, and abduction, people don't talk about it very much because it's a monster that's hard to really attack for a long time in AI. But the truth is, everyday human inference is abductive reasoning. And that's really what's critically lacking with AI, without which AI cannot really have this robustness that humans have. Like when we encounter previously unseen situations, we tend to be pretty good at doing the right thing. Even driving, we learn to drive really fast. We don't have to do all these like tail cases, like previously unseen cases. And, what do you do with this human, that human of all sorts, wearing crazy outfit. And we don't need to see any of that. And I think there's something really fundamentally lacking in current AI, which is too task specific or even data set specific, not even solving the task, but solving only the data set. Because it's learning all this without learning the proper conceptual knowledge about how the world works. So I'm trying to get to that more basic knowledge, but it turns out it's a really broad spectrum of knowledge that we know about the world. And when we want to go for the broad coverage, language becomes very important as a medium for reasoning, medium for understanding between machine and humans. So when humans want to check whether machine really knows something or not, language is the best communication medium with the machine.
And so going beyond or digging into the common sense reasoning a little bit more, you pursue research into a couple of, I guess, sub areas there. One is physical common sense reasoning. The other is social common sense reasoning. Can you describe those efforts?
Oh, yeah. So, yeah, I think both are very important. So physical common sense reasoning requires perhaps more of the physical grounding as well, perhaps with vision and robotics. And so for that, I also work on grounded learning of language or grounding with computer vision signals and trying to learn the mapping between the two. And then for social common sense reasoning, I think it's really important for AI to actually understand humans, like how humans interact with each other, and then be polite, be reasonable, be fair. And now we're entering this social norms and moral norms as well, because that boundary is not that distinct. Some of our social common sense knowledge, sort of like, for example, it's rude to turn on blender at 5 a.m. if you're living with a roommate. Unless the roommate wakes up at 4, but in general, 5 a.m. But it's not as morally bad compared to maybe stealing your roommate's money. I mean, probably like there are many things that are immoral, and there's like relative strength of their immoral or moral implications. And again, all of these are best described through language. And so I worked on paper, I think it was published last year. So it's called the Social Chemistry or Social Chem 101. And it has a lot of annotated rules of thumbs of social norms, moral norms, ethical norms. And in terms of ethics theory, it turns out this line of research that philosophers do, there's something called the descriptive ethics. And this is when people ask, or researchers ask people, what would you do if your roommate ran blender at 5 a.m.? Probably don't kill the roommate just because of that. So this is like asking in a concrete situation, what would they do? And we built that symbolic knowledge graph. And then again, we did something similar to COMET, which is to build social norm transformers to see whether they can reason about previously unseen situations. And again, we were seeing very promising results there. And I think that should really be integrated into, ideally, for example, dialogue systems in the future, because currently the dialogue agents can be agreeable with anything. Even if you say, I'm going to kill myself, it might just cheer you up to do that. Or if you say something really questionable in terms of ethical judgments, it might just be agreeable. But all of that should change. And for that, we need a model for social norms, moral norms as well.
I'm thinking about examples like this Tay chatbot that learned all kinds of
Yeah.
racist things
Yeah.
and the like. And it sounds like what you're saying is that this is potentially a way for us to model kind of societal norms and I don't know, filter is the right word, but kind of whatever other models we build, kind of use something like this in conjunction to give the model a sense of appropriateness or whatever
Yeah,
the right
absolutely.
term
And
is.
it's a little bit similar to, I mean, like when we think about what would GPT-2 and 3 know, well,
Mhm.
they read everything, including Reddit and everything,
Right.
including fake news and everything. So, of course, then it's going to spit out that kind of a language. And I don't think the reason why it's saying all this biased stuff, racism and everything, is because it's not larger in, it's not large enough. It's not the scale that will fix this bias or morality issues or ethical issues. We just need to teach them what is correct and wrong in the way that we teach our children. We, tell children we shouldn't do this. That's impolite. We shouldn't do
Mhm.
that. That's unethical. We're willing to teach all of this to humans. I think we should more than willing to teach this to machines in the declarative form so that the machine knows what's right and wrong.
Mhm. Mhm. And so at the same time, it jumps out at me that there's incredible challenges with generating ground truth that you might need to train a model when, as humans, we don't agree on in absolute terms as to, for example, whether turning on your blender at 5 a.m. is better or worse than leaving a dish unclean in the sink overnight or something like that.
Yeah,
Like
yeah,
there's no clear hierarchy for
yeah.
most, if not many, if not most of these scenarios.
Hmm.
How do you address that kind of ambiguity in your work?
Yeah. So that ambiguity is what excites me the most because I realize that humans are weird, complex beings who are somehow able to navigate through all that. And even though you and I may not agree which is worse between the two, at least you and I agree that probably not everybody will agree with my decision. So we have this sense of whether don't kill people. Okay, this one is probably easy for everybody to agree with. But even so, of course, there's always some counterexample somebody can come up with in some culture. Maybe it's totally fine to kill your daughter if the daughter was raped by some other man. So I disagree with it, but there's such a culture that does exist even in actual human societies. So it's a challenge, but the way that I address that, me and my students address that in our work is by incorporating all of that by asking a lot of people. If you ask a lot of people, their disagreement naturally arise in their annotations. And also we can even ask them directly, do you think this is what everyone would agree, or is this more discretionary question? And so
Mm.
then we get that kind of information, and then the AI then learns that for this situation, the answers are more like distributed across different labels, whereas for this one, it's very skewed onto one thing.
Do you think as humans we are good at knowing when other people may disagree with our worldview?
Reasonable. I mean, reasonable. It's not perfect. It's not perfect. We never are perfect. By the way, humans
Yeah.
are not perfect. Humans are confused all the time. I mean, climate
Nice.
change even. Ugh,
Yeah. Yeah, exactly.
yeah.
You recently did a keynote at the Stanford HAI Foundational Models Workshop. I'd like to have you tell us a little bit about your talk there. But before we do, tell us a little bit about the Foundational Models Workshop. What was the goal of that session?
Yeah, so that workshop was quite impressive. It giving a lot of attention to basically pre-trained neural models. I think they focused a lot on language models in terms of the speakers who were speaking at the technical session, but I think they meant more broadly any neural models trained on large amount of data that serves as almost like a foundation for other downstream applications. And
Hmm.
so my talk title was David and Goliath, the art of leaderboarding in the era of extreme scale neural models, because this becomes a bit of a, as the neural models scale becomes extreme, I would say I do get a lot of extreme questions from students or journalists asking me, these are actual questions, asking me whether we will achieve AGI by scaling things up. Maybe nothing matters but scaling things up. So another extreme question that I often get is, oh, what are we supposed to do in academia? Should we just all go to these companies where people are scaling things up? Can we do anything impactful from academia? So the talk was counter argument against it because, time and again, it's not always the case that the winner stays winner forever. The giants, there's always new innovations coming from the younger generation. I find it really fascinating. Why is that the case? And new startup companies are becoming the successful companies, and this happens all the time. It's not the case that the same company always win all the games and keep innovating. So I do think that there are a lot of things beyond the scale. But one easy counter argument that I like to make is that, we cannot reach to the moon by making the tallest building in the world 1 inch taller at a time. We just can't. We have to have entirely different game plan. So similarly, I don't think scale alone will do it, though scaling laws are real in that it's like denial is almost, you cannot deny it. It's like, it's there, it's real. It's futile to deny it. However, we can be more efficient. We can sometimes even win larger models by incorporating different richer learning signals that can include even grounded learning in the 3D environment or grounded learning with the images and videos. And then we can also do better knowledge integration, symbolic knowledge integration. And so that was part of my talk as well. And last not but least, algorithms used to be at the core of computer science. Or at least when I was a PhD student, it felt in some sense more intellectually beautiful because there were just more equations and more algorithms in our papers. And I think that can come back. It's just that we cannot use the same kinds of algorithms. We need to develop better inference time algorithms for neural networks so that it can do reasoning that neural networks are very bad at. So when talking to you earlier, I was talking mostly about just spitting out one word at a time, which doesn't feel like hard reasoning or even correct reasoning. But in our other work, we also do more of this constrained algorithmic inference or reasoning, where given logical constraints, I have to go with the algorithm can then do this hard constraint satisfaction that might be hard for humans, might be easy for humans depending on the scale of it. But we found that if we do that, we can beat larger scale neural models with smaller scale neural models with the power of algorithms, logical constraints, logical reasoning. So I think that there are a lot of underexplored things there, but one could always argue back that, well, even the larger models can benefit from the the logical algorithms, and that's true. If something is already so good, it's just that when something is so good, so big, so that it's like GPT-3 big, then most people cannot actually download the model and use it, or most people don't even have access to it. So there's, I think, real needs for making smaller models more powerful at the moment. And so the talk was about that as well.
Does reasoning, in the context that we've talked about it, do you think that it requires ultimately some kind of symbolic or algorithmic component, or is it possible to do it wholly statistically?
I believe in combination of both. I think statistical or neural approaches can handle some aspects of reasoning really, really well, but I don't think it can handle what's 2 plus 3, that's 5. Like the factual, real symbolic reasoning is much harder. And on a related note, I do not believe the neural network, like sequential, just a neural method without actual integration of mathematical concepts, can learn to do mathematics correctly. So, how many days in a week? 7 days. So let's meet a day after this week instead of this Tuesday. When we do, for example, 2 days before Christmas, we know what I refer to by that. Neural network may not be able to. And all this like simple symbolic reasoning is really brittle right now with neural models. And I think there has to be some sort of a rule symbolic integration into neural network going forward.
How effective are the ways that you or others in industry are doing that now? Where are they most brittle? Where are they strongest? Like what are the most interesting things in that integration at those integration points?
Yeah, so the sort of things that I personally tried, so we call our algorithm as neural logic decoding because it's a combination of neural stuff with logic constraints. We take conjunctive normal forms as the logical forms, as the basis of logical forms, and then go from there. And we developed discrete search algorithm. In some sense, the classical search, that was like textbook, AI textbook in the early chapters. It's all about search, A star search. And so it's a search algorithm. And that's one way to handle it. But in doing so, I realized the following, which is that the evaluation benchmarks really drive where people focus in terms of research. So if the evaluation benchmarks do not require such logical reasoning,